welcome home. Good morning. I just want to thank the leaders of this initiative, Dr. Jihad Touma from Physics, Dr. Nader Bizdi in Islamic Studies, Philosophy. It's one of the initiatives that is a leading model really for AUB and for the Faculty of Arts and Science in particular, doing the physics with the arts and the humanities, crossing to other faculties, into engineering, into agriculture. These are the kinds of initiatives that are rare to happen, and I'm very happy that Dr. Touma and El-Bizri have managed to sustain, frankly, this initiative for a whole year. The Year of the Moon, they called it Al-Amar Bimoon, and they took it outside doors of AUB as well, all the way to Mashghara. So really, thank you very much for doing this and for being so inclusive and so interdisciplinary. We talk a lot about that, but we do very little of it. So thank you again, and I wish you a great conference.
Thank you, Dean Sheikh, for these introductory words. I'm Jihad Touma, and together with Nader Bizri, we had put together this feast around the lunar year. I will leave Nader to tell you more about the activities that were structured, and I try to tell you a bit about the genesis of the workshop that we're kicking off today. I'll be lying if I say that I've been really dying to have you all with us for some time now, because when I wrote my last article on the moon, I thought I was done with the moon. I was done with dealing with any objects that are so close enough that we have so much data about them that the work is arbitrarily exhausting, not to say arbitrary in some aspects. The other work that we do is, of course, arbitrary, but there is no one to check us on it, at least not while we're still alive. So that's out of the way. To say something about the origin of the workshop is also easier than saying something about the subject of the workshop, which is the origin of the moon itself. While there is much controversy and paradox associated with the subject of the origin of the moon, to me it's perfectly clear how this thing came about. I was actually visiting Princeton in 2017, and Scott comes up to me and says there is popular demand for you to tell us something about the moon. People deal with all sorts of complex things, but this very complicated thing is somehow not passing through to them. I said, do you really want me to do that? He said, think about it. And then a day or two after, I was having dinner with Professor George Saliba here, who also maintains residence in Princeton. And I was telling him about the subject of the talk, potential subject of the talk. And then I realized that the evaction, which had occupied myself and my then PhD advisor, Professor Jack Wisdom, the evaction is actually at the heart of much of his work on the history of science. And then I thought, okay, now it's starting to look very interesting. And particularly interesting since we were very lucky for George to consider coming back to AUB, having held a prestigious position at Columbia University in New York. So all of this started gelling. And I said to George, should we start planning from now? And George said, let me get to Beirut first. And then, okay, I kept it at that. I delivered a historical review of the evaction to my colleague in Princeton, which went reasonably well. And I tried to revive some of that for you later this afternoon. And then once back, I connected with Professor Nader Bizri of History of Science and Philosophy, and then realized that he as well has been looking at manuscripts dealing with optics, and particularly the light of the moon in the works of the famous Ibn al-Haytham, otherwise known as Al-Hazm. So, to Europeans, that is. So, Nader and I exchanged thoughts, and we decided, okay, let's do it. Let's go for a full year dedicated to the moon, interpolating between disciplines, engaging architects, and we'll tell you more about that, leading up to a workshop, which for me, as an astrophysicist, planetary scientist, who's again looking at planetary systems with a number of colleagues, some of whom are in the audience from neighboring universities, thought that, okay, maybe it's about time that I make my peace back with the moon, with the Earth-Moon system, and find out from people who have been leading the efforts in the astrophysical end of things, where things stand actually. And I had to do a lot of homework in preparing for the workshop, and I'm sure I'll have a lot more work to do once it is over. So I'm very much looking forward to this conversation. We've gathered planetary scientists, leading geophysicists, planetary geologists, dynamicists, all in one way or the other having been touched by the curse of the moon. So without further ado, I will let Professor Nader Al-Bizri tell you a bit more about the initiative, and then we proceed with this morning's session. Welcome, everyone.
Good morning again, and welcome to you all. It's a great pleasure to have you with us here at AUB. Actually, there were multiple factors that made me become engaged in this initiative. One of them was the idea of collaborating with a physicist and a dear friend, Professor Jihad Touma. And this comes in line with the initiative that we are leading at AUB now in terms of revamping our general education and establishing a new core curriculum in the liberal arts. So in the spirit of that initiative, I thought it would have been a great opportunity to find ways of finding synergies across faculties and in terms of disciplines. So we started thinking about structuring a series of events for the year in terms of activities that celebrate the moon from multiple perspectives, coming from the arts, the sciences, the letters, and trying to engage partners from various academic units across the campus. So the beginnings were with a sort of an attempt to introduce the initiative via the Azarkian School of Astronomy that was held about a year ago here at AUB. And it was in a lecture that addressed a bit aspects that relate to moonlight and optics. But then we moved to having a sort of a focus that is more rooted in cultural aspects and socio-political. So we considered that this initiative itself comes in line with the 50th anniversary of the Apollo 11 manned moon landing. And in that regard, we wanted to see what was happening at the eve of that momentous event on campus at AUB. So we had with us Professor Fawaz Trabulsi, who told us about the activities that were taking place on campus at that time, which seemed that the preoccupations with social political issues were more at the forefront of the interest of the students on campus. Then we contacted a colleague, Dr. Karim Najjar from the Faculty of Engineering and Architecture, and he established a whole studio theme. He gave it the title Lunatopia, and there were designs proposed by his students in the course of the whole semester for establishing a moon colony. And we had the privilege of being present ourselves in the studio and following up on the pinups and eventually in the jury. And the activities continued in terms of Dr. Touma having a sort of a lecture that popularized the science in the context of university for seniors. So we wanted to go beyond just the regular engagement within the context of academic units to engage other programs within the university. And we had also additional events that culminated in a beautiful gathering that we had in Mashghara and the Zaki Nassif Center that combined a lecture on the moon with music and actual sightings of the rise of the moon from behind Jabal Sheikh, which brought lots of partners that were beyond the walls of the campus. And now we have this workshop as a culmination of this year of lunar activities. And that will end also with a concert in highlighting again the kind of multidisciplinary and the spirit of the liberal arts that has guided us throughout this year. And thank you very much for all the speakers for being with us here on campus. Thanks.
Okay, just to give you an idea of how the workshop is structured for the next 3 days. So actually 4 days. So we'll have morning, afternoon sessions dedicated to the moon, its dynamics, geophysical constraints on formation and formation models. And then at 4:30 on today, Tuesday and Thursday, we will have public lectures. Today's public lecture will be delivered by Professor George Saliba on Ptolemaic cosmological considerations in relation to the moon, problems with them, and how they fed into Islamic science, and then a renaissance with Copernicus. Tomorrow we'll have a public lecture on the light of the moon by Professor El-Bizri. And Thursday, we're delighted to have Professor Alessandro Morbidelli deliver an installment of the Bellamy series of lectures in the natural sciences. So we're very excited about these. Today, I've asked our, what should I call them? Yes, my friends. Yes, I asked my friends to, if they would be generous enough to give us overview lectures to set the context for our whole meeting, and they were kind enough to oblige. So we'll start with an overview or a review lecture by Dr. Simon Locke on the formation of the moon, and then we'll move on to a lecture by Professor Jack Wisdom on tidal evolution of the Earth-Moon system. It will be one in a series of lectures delivered by these two gentlemen. Simon will follow up with a technical talk on his most recent and very exciting proposition for lunar formation scenario. And Jack will give 2 more lectures dedicated to elaborations on the dynamics of the evolution of the moon, starting with various initial conditions dictated by increasingly popular formation scenarios. So Simon came to us from Caltech, where he's the planetary science postdoctoral fellow in the Division of Geology and Planetary Science. He finished his PhD at Harvard University, having completed a BA and an MS degree at Cambridge University. He is a specialist in planet formation with focus on the solar system and exoplanetary systems. And this morning, he will review for us this whole business of lunar formation. Simon?
Oh dear. Good. Good morning, everyone. So, as Ishia had said, I'm going to review some of the recent thinking about the formation of the moon. Well, some of the very old thinking, some of the more recent thinking, and then also look at the way forward in terms of what's next for trying to understand the formation of our nearest neighbor. So, given that we're a whole range of different people, I thought I would start with introducing myself, but she had mostly done that. I just want to stress that, so the way I approach problems in planet formation and evolution is to try and understand the underlying processes that are at work. So, for me, looking at moon formation is a way of actually having a very well-constrained problem that we have a lot of data on, which makes it very hard, but it also makes it very insightful as sort of a remnant of planet formation that we can actually, we have stepped onto, but also can observe from orbit very easily. And so we have a lot of information. We can actually use it as a window into planet formation and planet formation theory. And so that is one of the reasons that why people who do what I do care about how the moon formed. So part of it is it's the nearest thing. It's very important, certainly for life on Earth now, and probably was very important for establishing life on our planet. And it's sort of just one of those very interesting problems that's fascinated humanity for a very, very long time. So there is something of a plethora of different lunar origin theories, and today I will be concentrating mostly on what is known as the giant impact hypothesis, but I thought it would be remiss not to mention the various other proposed theories. The first of which is capture. So basically, the proto-Earth is just flying around its orbit. Something gets a bit too close, gets sort of captured into orbit around the Earth, and over time, that orbit slowly gets circularized, and you end up something with the Earthling system we see today. Another is that maybe that object that's flying past got a little too close, got ripped up by the tides from the Earth, and then out of that material, the moon formed. You can also, all suggested by George Darwin, grandson, I believe, son of the famous Darwin, suggested that maybe for some reason the Earth sort of popped out, the moon sort of popped out of the Earth at some point for various different mechanisms have been proposed, investigated. And the other one I'll mention is something called binary accretion. So this is the idea that both the Earth and the moon formed at the same time around each other, similar to sort of what's thought to happen for, maybe thought to happen for some of the giant planets and their systems. And the one that has got most attention and what I will focus on today is what's known as the giant impact hypothesis. This idea that that thing flying past the Earth wasn't so lucky. It didn't just get disintegrated, it actually hit the proto-Earth, spewed out a load of material out of which the moon formed. And this has become the focus of lunar formation studies, basically because it is the most successful at matching a lot of the first order observations of the Earth-Moon system, although we'll get into more of the technicalities of that soon. And also it's been shown that a lot of these other mechanisms either are just physically not reasonable, or would require very special conditions and very special requirements to actually make them work. So for today, we're just going to focus on the giant impact hypothesis. So one of the reasons that the giant impact hypothesis is quite attractive is that it is a natural outcome of what we think is the way that planets formed, at least in our solar system. Although I'm sure Morby will talk, Alessandro Morbidelli, we nicknamed him Morby. We'll talk about more about this later in the week. But the basic theory of planet formation is in our solar system is that planet formed by collisions. You start off with a disk of gas and dust around the protostellar object, and over time, which is wonderfully imaged by these Alma long baseline images. This is actually one of the more older ones. There are many more available. But you start off with this gas disk, gas and dust disk. By some process that we're still only really beginning to understand, they assemble into sort of asteroid-sized objects. This is why this is magic. Which collide together to make oligarchs, which collide together to make embryos. These are planets, these are quite large bodies. We typically, in our solar system, think of them as being sort of Mars mass, around Mars mass, due to the isolation masses in our solar system in a standard solar nebula. And these bodies continue to grow. The largest bodies have the largest gravitational attraction and so grow faster than the ones around them. And eventually you grow to make protoplanets. And the last stage of this process is when these embryo-sized bodies begin to collide together. And this stage is what we refer to as giant impacts. Now, there are various other processes happening during this time. You have a lot of accretion from smaller bodies as well, and the balance between accretion of large bodies and accretion of smaller things is an ongoing debate. But certainly in our solar system, we see lots of evidence for this final stage of collisions between planet-sized bodies. And these collisions are incredibly energetic. For the Earth, for a collision that forms an Earth mass body, more energy is released during the time of the impact than from the surface of the sun. So this is a very traumatic event for these bodies. A large fraction of the planets get melted, well, most of it gets melted, if not all, and a large fraction is vaporized. So you actually vaporize rock, which is not something we're used to thinking about in our everyday lives, thankfully. And also there are huge torques involved in these impacts because most impacts are off-center, and so you can actually leave the post-impact body very rapidly rotating with days of as little as a couple of hours. So it was proposed by two independent groups in 1975, 1976, that one of these impacts could actually form the moon. So the basic idea is that you have a body, generally called Theia, as the mother of Lunar, and that collides with the proto-Earth, spins out a disk of material around the Earth, and that is, out of that material, forms the moon. And it's a very simple concept and very much more complicated in practice, as we will see. But this is generally thought to be the last major event in Earth's formation. The moon-forming event sort of marks the end of Earth's accretion and sort of main stage of accretion, and sort of begins the later evolution, which eventually forms our planet. So this was the basic idea. And when computers caught up and we were able to model this impact using hydrodynamic, fluidynamic simulations, it was shown for a number of different modeling studies that there was a sort of preferred class of impacts. And that, basically, this is very simple. There are three main physical sort of first order constraints on the formation of the Earth and Moon. Firstly, you need to get the masses of the two bodies right. You need an Earth mass body and you need a lunar mass body. Seems so straightforward. You also generally require, although we will see this later, from your first page of, well, not first page, but your 101 physics textbook, that the angular momentum of the Earth-Moon system must have been conserved over time, because for a very long time there was no known mechanism by which you could change the angular momentum of the Earth-Moon system. Although, and we'll hear a lot about this week, different mechanisms by which it could happen or not happen. But this was sort of seen as a fundamental constraint, that the angular momentum of the system, so that the spin inertia has to be the same after the impact as it is at the present day. And finally, one of the mysterious things that's been known about the moon for a very long time is that it has a much smaller core, its iron core, as a fraction of its mass than the Earth. So using these three constraints, a series of studies led principally by Robin Knupp, who's now at Swery, found that there was quite a narrow range of impacts that would actually be able to meet these constraints. And that is of a Mars mass body hitting a proto-Earth at around the escape velocity and at an impact, sort of grazing impact. And it's actually sort of has led to this idea of a canonical impact. Because it's very fortuitous, there seems to be a very narrow range of potential impacts. This has been very useful for both geophysicists but also geochemists, because we could basically say, if we have to match these three constraints, this was the last impact the Earth experienced, and that allows you to make a lot of inferences about Earth's history, its chemistry, etc. So one of the great things that happened from the 50th anniversary of the moon is that you get lots of people contacting you wanting to make documentaries, planetarium shows, and so now we have some really fancy graphics to show you about what giant impacts would actually sort of have looked like. So this is a simulation which was made by these wonderful people. It's based on one of the simulations by Robin Knapp, and this is a visualization of what the canonical moon-forming impact would look like. So you have the Mars mass body coming in, striking the proto-Earth, it sends a huge shockwave through the Earth, and what happens is, because this is a grazing impact, the body sort of almost gets away. So it gets smashed up and it's trying to escape, but it can't, and it eventually comes back and hits the proto-Earth again. And what you're seeing here is sort of colder material that is being spun out around the proto-Earth, and this material and some later ones that will be added by the collision of the impact will actually be the material that ends up forming the moon. So I should point out that this is not entirely realistic, because you would be currently writhing in pain, having had your eyes burned out of their sockets, because the temperature of some of this material is tens of thousands of Kelvin. But this is nice. We've let you see what's happened inside. Well, the animators have let you see what's happened inside that horrible blinding gas. Yeah. So you can see that this material, you have various small blebs of material that get sheared out and placed in this disk of material. If you want to watch the whole continued sequence, you can find this online with interesting commentary. So we have a post-impact planet with a disk of material around it. What happens next? So you have, in the canonical impact, what happens is you have a planet, which around it, inside what's called a Roche limit, which I'll explain in a second, you have a disk that is a mixture of liquid and vapor rock, predominantly, with small fractions of metal, which is actually likely dissolved into the silicate at this point because it's so hot. There is some boundary between the planet and the disk, and this is something that we're not really sure what is happening here. It is a very complex, both dynamic and thermodynamic boundary, and there's sort of, this is one of the main areas that I think there's a lot of uncertainty and more work is needed. But for now, as most models have done, we're just going to treat this as a hard barrier, that you go from the disk to a surface of the planet with nothing in between. And then further out, most of the material in the disk is condensed, or very rapidly is condensed by radiation after the impact. And the boundary between these two is generally placed somewhere around the Roche limit. So the Roche limit is a very important concept for those of you who aren't familiar with it from other astrophysical applications, because anything inside the Roche limit, if they try and form a large body, they will be ripped apart by tidal forces. Basically, the gravitational differential, the differential of gravitational force between the two sides of the body due to the Earth is greater than the gravitating force of the body itself. And so it gets ripped apart and smeared out into much smaller fragments. Whereas outside of the Roche limit, you can actually have a large clump of mass surviving. And so this is incredibly important, obviously. If you want to form a moon, you have to form it outside of the Roche limit. So in canonical giant impacts, generally not enough mass is in place beyond the Roche limit to actually form a lunar mass moon. And so material, in order to form a large enough moon, has to be transferred from the inner disk out to beyond the Roche limit through viscous spreading or dynamical instability in the inner disk to push material out, both onto the planet, but also out beyond the Roche limit where it can accrete to the moon. And there has been a lot of work trying to model the various different parts of this process. Probably one of the more advanced sort of holistic complete models of this is this one by Julien Saman and Robin Knapp in 2012. And what they did is they divided the disk into these three sections. So you have the protoplanet, you have the inner disk, and you have an outer disk. And they treated these different sections with different simulations, treating the different physics in each. And now I should point out that we need these. I should have pointed out that these models, we need different models to look at the formation of the moon, because those simulations that we use to do the actual giant impact are very good up to a day or 2 days after the impact, but actually lack a lot of the physics that's needed to capture the formation of the moon itself. And also, the moon forms over periods of years, and if you want to run a giant impact simulation for years, you will need a very large supercomputer and a lot of patience. So we use more parameterized simulations to actually look at how the moon forms over time. And what Julien and Robin found is that there's sort of 3 stages to lunar formation. So the first is, because outside of the Roche limit, you can very quickly collect mass into larger bodies, you end up with forming a sort of proto-moon in a matter of months. But then there is sort of a pause while the inner disk actually starts to cools and spreads and starts to eject material outside the Roche limit to accrete, to form, to add on to this proto moon. And so you have a small delay, and then you continue over tens to hundreds of years to actually continue to form and add mass to the moon. And throughout this time, and then through the rest of history, tidal interactions this early between the moon and the disk, and the moon and Earth, and those tides have continued to the present day. The moon is slowly moving further and further away from Earth, and sort of eventually it's sort of cut off from the supply of mass from the inner disk. The inner disk cools and probably likely all collapses to the Earth. And this process of tidal evolution has continued to the present day, and I'm going to talk no further about it now. I will leave that to Jack and his introduction and the rest of the talks this week. But eventually, through tidal evolution, we end up with our situation today where we have the Earth and the moon. This is to scale. I love this image. It's a very long way away, not far from the ecliptic of the sun. So, all's right and dandy. We know how the moon formed. If that was true, we probably wouldn't be here. So the problem with moon formation is that there is always more data. And there is also, as we have got further on, there's also been improved numerical models. And so as we have learned more about the moon and learned more about the process that formed it, it has become apparent that there are some issues with this canonical model of moon formation. And I will not give you an exhaustive list here. I will just highlight 3 of them, what I think are the most important. And first is one that has always been a challenge in moon formation. The ratio of mass between the Earth and the moon is largest of all of the terrestrial planets in our solar system. I mean, the only other example we have is Mars, where the moons may have been formed by a similar process, but are much, much smaller than the host planet. And actually getting enough mass, and particularly angular momentum, out into a disk with the constraint of the present day Earth-Moon angular momentum of the system is actually very challenging. So, as I mentioned before, we don't directly form the moon in our giant impact simulations, and we have to rely on what we call scaling laws that convert the mass and angular momentum of material that is placed in orbit in a giant impact simulation to the mass of the moon that would eventually be formed. So these look like fun plots like this, and this one is from that paper I showed earlier by Julien Sommer. And what you're looking at here is the mass of the moon that you form as a fraction of the mass of the disk, as a function of the specific angular momentum, so the total angular momentum divided by the total mass of the disk in a convenient set of units. And what you see here in these triangles, the results of all of their disk modeling simulations, and what you see is that generally only a fraction, less than 50%, of the mass of the disk actually makes it into the moon. That's because a large fraction of that actually ends up just accreting to the Earth in order to conserve angular momentum of pushing material out beyond the Roche. But what you can see here is that there are sort of two different lines. So these black lines are from studies that basically assume the most optimistic form of efficient path to forming the moon, and they're found by n-body simulations. So these are basically, you take all your mass, divide it up into little point masses, and let them evolve under gravity. And what you basically find is that when you do that, you basically have angular momentum conservation, very little mass is ejected from the system, and so a relatively large fraction of your disk mass is converted into the moon. What Jean showed in his paper is that including more of the realistic physics and the complications that come by adding a multi-phase inner disk, you actually end up with less efficient accretion. And this is an issue because in all of our giant impact simulations, we're very optimistic people, and we use these black lines. And so we take our giant impact simulation, take the mass of the disk that we form, and say, oh look, we formed a lunar mass moon by using these scaling laws. And so if you look at the literature and plot a histogram of the fraction of impacts that form a given mass satellite, what you find is using the n-body scaling laws, there are a large number, I'm going to forget the number, several hundred different published giant impact simulations that would form a lunar mass moon or above. However, if you use one of the more realistic, well, you can argue realistic, more conservative disk formation model, what you find is there is actually only one published giant impact simulation that would form a lunar mass moon in this less optimistic scenario. So there is a lot about disk dynamics that we do not understand, and where we are in this range of accretion efficiencies is still an open question. But it is worrying that the most recent simulations of moon formation would not actually allow, or it would be a very unlikely situation to have a lunar mass moon from a canonical moon forming impact. So this is a point that I won't really discuss much more, but this is a very much a focus of my thought, at least going forward. So yes, so due to the complicated physics of disk evolution, the forming a large enough mass moon is challenging. So secondly, one of the outstanding observations which we've known about since the days of Apollo is that the moon is depleted in what we call the moderately volatile elements compared to Earth. So I think most people in this room are more astrophysics based, so I'm going to scare you and show you some geochemistry. It's not very hard. But basically what this is a depletion factor. So this is the amount of an element in the moon relative to the amount of that element in the Earth. And what has been known for a long time from this is paper was one of the first to sort of do it for a lot of elements, compiled for a lot of elements, Ringwood and Keeson in 1977, is that the moon is depleted by orders of magnitude in various elements, things like potassium is particularly favorite, copper is somewhere here, germanium, relative to the Earth. So at some point in its formation, for some reason, the moon acquired a lot less of these more volatile elements than the Earth. Or alternatively, the moon had these more volatile elements and then lost them out of the system after it formed, or during its formation. And what this has largely been interpreted as is requiring a high temperature formation for the moon. And this is a very powerful constraint. You have lots of data points, and it is a very complex thermodynamic system, but there has been, although there have been suggestions as how to have the moon be more depleted in moderately volatile elements through a high temperature origin, there's been no study that's actually been able to quantitatively match this depletion. So, moderate depletion. So this is still very much an open challenge in lunar formation. And finally, the thing that has sort of obsessed the field for the last, I'd say, 15 years or so, has been that the Earth and the Moon, as well as being similar in their non-volatile elements or non-moderately volatile elements, are also similar in the isotopic ratios of various different elements. And that is significant because we tend to use various isotopes, for example, most commonly oxygen. So this is the mass-independent fractionation in oxygen isotopes. So this is for various different bodies in the solar system. So this is the moon. This dashed line is the Earth reference. So by definition, anything that's close to zero is close to the Earth. You have Mars up here, found from studies of Martian meteorites. And you have different asteroidal bodies, again from meteorites, angaroids, and nuclides. The important is not the different bodies here, but the important thing to take home is that what we typically do is we use things like oxygen and other isotopic systems like chromium, titanium, and various others as fingerprints of where material came from in the solar system when it formed. Because we think these processes are set by the different sprinklings of different pre-solar material or from different processes in the disk itself, they record where material came from to build a body. And so what we would have expected is any body in the solar system would have have different oxygen, titanium, chromium isotopes. And so we'd expect the thing that hit the Earth, there, to have a different isotopic composition to Earth, to the proto-Earth, to Earth itself. And what we find in impact simulations is that 60 to 80% of the moon in the canonical impact comes from the impactor itself. And so we'd assume, based on this, on our previous knowledge of the solar system, that the moon and the Earth would look very different. However, what we find is that within error of very precise, very, very precise modern isotopic measurements is that they are the same or very similar. So there is a slight debate in literature as to whether they are identical or very slightly different. This is the most recent by Greenwood et al., arguing that the moon here, the Earth here in blue and the moon in orange are just resolvable to within error. I believe there are 9 statistical tests in their paper, 5 of which confirm that they are different and 4 of which say that they are the same. So depending on where you want to stop reading the paper, you can make your own conclusions. But similar results are found in for different isotopes, which are measured admittedly slightly less precisely than oxygen, things like titanium, silicon, chromium, iron, and onwards. But more curiously, in some ways, the moon is also the same in elements that are not fingerprints of where material came from, but more the processes by which planets formed. This is the elements to which I'm referring to is principally tungsten. So tungsten is produced, 182 tungsten is produced by decay of 182 hafnium, an element you've probably never had to care about in your life before. But the important thing about these two elements is that hafnium and tungsten behave very differently during core formation. Hafnium goes into the mantle, and tungsten sort of hangs around the mantle, but mostly goes into the core. And so if you have a core formation event, the mantle ends up with a lot more radioactive hafnium than the core, and so produces a lot more 182 tungsten relative to the non-radiogenic isotopes of tungsten like 184. And so the isotopic ratio 182-184 in the mantle goes up relative to that in the core. And so depending on the conditions and time evolution of core formation, different bodies end up with different tungsten isotopic ratios. And so again, even if the Theia and the proto-Earth were made out of the same material, because we would expect, because of the stochastic process that planet formation is, they would have different growth histories, and so should have different tungsten isotopes. But when we go, when some very careful and patient people, this plot is from Tabul et al. And Kuja et al. In the same issue, also found a very similar offset. What you see is that the moon is very slightly different from the Earth, but the moon has accreted a lot less material after its formation than Earth. And so accounting for that uncertainty, it is inferred that the Earth and the moon started off almost identical. So not only are they made of the same material, they seem to be made out of the same bodies that have gone through the same history. And so this has been a really big mystery as to how it's got. And as isotopic measurements become more and more precise, it's become clear that it's become a bigger and bigger problem. And so this has been the principal observation that people have been trying to explain in recent times. And there has been a number of different potential solutions, of which I will cover, I think 5, but there are several more that we can spend the rest of the day talking about. So the first is very obvious. Maybe we just don't quite understand the solar system. And actually, maybe there was a reservoir of material in the inner solar system which was all similar isotopically, out of which the Earth and the impactor Theia formed. And so they would have started off with the same isotopic fingerprints. And there is some evidence for this. There is a slightly eccentric class of meteorites called enstatite chondrites that in a lot of their different fingerprint isotopes look very similar. And so Nicolas Dauphin and Stein Jacobsen at the same sort of time suggested that maybe if we just start off with the Earth and the Moon having the same isotopic fingerprint, and the enstatite chondrites are sort of the rubble left over from this reservoir out of which these two bodies formed, maybe this would explain the fact that the Earth and the Moon are the same. So enstatite chondrite is roughly equal to both Earth and Theia. However, you then still rely on tungsten isotopes and the similarity in tungsten isotopes to basically be a coincidence. That this is just by chance, you got the right mixture, you got the right body, and they somehow ended up being the same. But recent studies have suggested this is actually an incredibly unlikely event. And so we now get into the debate of Occam's razor, which plagues this field in the sense of this is not necessarily a likely event to explain the Earth-Moon system. However, it is still a possibility. Secondly, a proposal by Raluca Rufu and co-workers suggested that maybe we've been hung up on the fact that the Moon was formed by one impact. What happened if it was formed by many? So what you do is you have a sequence of impacts, each forming their own smaller moon that accrete together to make, eventually over time, make our moon. And because you're combining multiple impacts and multiple impactors, maybe we just average out. Because the Moon is forming out of an average of the material the Earth forms out of, you actually end up with a roughly similar Earth and Moon. However, because the difference is so small between the Earth and Moon, you need a very large number of impacts to create moonlets. And then you have to have the Moon survive and all of the moonlets survive and accrete together after each of these impacts. And so this is a very interesting suggestion. This process is almost certainly is happening. You do have many small impacts that are forming small satellites, but the feasibility of actually growing something as large as our moon and still explaining the isotopic similarity is an open question. And thirdly, a very interesting suggestion by Kaveh Pahlavan and Dave Stevenson here suggested that, okay, you have a disk and a planet that have different isotopes. They have different signatures, but maybe we can just erase that signature after the impact. And what they suggested is that through that boundary layer that we're not quite sure what it is between the Earth and the lunar disk, you have exchange of rock vapor between the two, and you sort of average out the isotopic differences over time. The issues with this, I will talk a lot more about the issues with mixing in my talk later this week. But in order to actually erase the isotopic differences between the Earth and the Moon, you need to exchange an awful lot of material through a barrier, through multiple barriers, both angular momentum and thermodynamic barriers, to actually smooth out the isotopic composition. And you have to do this through a boundary that is trying to transfer angular momentum. And so it's sort of a very, it could be a very complicated process to actually be able to erase the isotopic similarity to the amount that you require to explain the modern observations. But we'll talk about that more later in the week. And then the final suggestion, which is really has been a very important development, is that maybe we can just explain away, we can just sort of circumvent the entire problem and not have a canonical impact at all, but have a much higher energy, higher angular momentum event, which during the impact itself has much higher shear. You actually mix more of the material together. And so just in the impact, you can sort of exchange material between the impacting bodies, mix the material of the two impacting bodies to actually produce an isotopically similar Earth and Moon. So the problem with this suggestion is that in order to have a different impact, as Robin Knupp showed, you need to change the angular momentum of the Earth-Moon system after the impact. And there's now been a number of different mechanisms which have been suggested to do this. So, and we will hear a lot more about that this week. But the possibility of changing the angular momentum of the Earth-Moon system, even somewhat after the impact, allows you to explore a much wider set of impacts than was possible just within the canonical model. And in 2012, there were two classes of impacts that were suggested as very good ways of mixing impactor and target material. The first on the right by Mattia Chuk and Sarah Stewart was that maybe if you had a very rapidly rotating pre-impact proto-Earth that was hit by a fast, small impactor, you would actually just basically blow off part of the proto-Earth's mantle into orbit and form the Moon out of that, with very little impactor material involved anywhere in the process. Alternatively, Robin Knupp suggested you could have two half-Earth mass bodies collide, and the great thing about two half-Earth mass bodies is that you basically have a symmetric impact, and so end up with very efficient mixing of the two bodies. So again, thanks to Adler Planetarium, I can show you fun, exciting animations of these. So this is, I'm going to show you an animation of the suggestion by Mattia Chuk and Sarah Stewart. So here you have a very rapidly rotating proto-Earth, very oblate, being hit at high velocity by a small half Mars mass impactor. And this basically just seriously screws up the planet. And you end up with a much more rapidly rotating post-impact planet. And this thing is much higher energy, so you actually end up vaporizing tens of % of the body. Actually, after these impacts and after the canonical impact, there is no surface to the planet. It is basically a silicate gas giant. You go from a vapor atmosphere to a supercritical mantle to liquid at the very bottom, or towards the bottom of the mantle. So, yeah. But in order to get the high degree of mixing that you require a priori to get the isotopic similarity the same. In current impact simulations, what you find is there are very specific impact parameters to actually form an isotopically similar Earth and Moon. And so a lot of the debate about these suggestions has been how likely these different initial conditions are in moon formation. However, one of the very interesting things about higher angular momentum, high energy impacts is that they actually don't end up producing the sort of traditional image of a disk and a planet. What you end up with is basically a structure where those two parts, the planet and the disk, become connected. And so you do not have a dynamic and you do not have a thermodynamic barrier between the planet and the disk. And this was most of my PhD thesis, smashing my head against this problem. And what we found, what we proposed is this is actually a new class of planetary objects called synestias. And there are a range of giant impacts, actually a large fraction, depending on how you define giant impact, which is key, a large fraction of giant impacts actually produce synestias. And I will talk a lot more about this later in the week and explain what a synestia is. But there's a range of different impacts which form these bodies, including the two proposed, previously proposed high angular momentum impacts, although it was not recognized at the time. And the important thing about this is this provides a very different environment for moon formation. Instead of forming the moon outside the Roche limit, surrounded by near vacuum, you actually form the moon inside the vapor of the proto-Earth surrounded by tens of bars of silicate vapor and several thousand Kelvin, which actually cooks in the moderately volatile element of the depletion of the moon that we see. The other thing is that the moon is forming out of a much larger fraction, mass fraction of the planet. And so you have a lot greater opportunity to mix, although as I will talk about later in the week, this is not a silver bullet to the isotope issue. There are still issues with mixing sufficient mass to actually explain the isotopic similarity between the Earth and the Moon. So, in summary, this is kind of where we're at. The giant impact theory is by far the most successful theory for explaining the origin of the Moon, but we are having some teething issues in explaining some of the both first order and also second order geochemical constraints on the formation of the Earth-Moon system. And so at the moment, we're at a very sort of exciting time in the field where we have a number of different propositions, all of which are potentially part of the problem, a part of the solution, but there is really no consensus on what is the correct model, which is sort of a scary time for having been very settled for a long time that the canonical impact was great, all fair and dandy. We now actually have a large range of potential moon-forming impacts to explore. So I just wanted to take the last few minutes. How am I doing for, I don't know, I forgot when we started. Just to talk about where we go next. We have all of these exciting possibilities. Where can we really try and look to try and tease apart which of these scenarios is correct and actually which of these scenarios is actually feasible? So the first is new data. So we are at a very exciting time because various countries, including most successfully currently China and the US, as well as small emissions attempts by India and Israel, we actually have a number of people that are planning to go to the moon to do a number of different things, but importantly, to do sample return. So all of the samples we have from the moon, well, not all, most of the samples we have from the moon are from the Apollo missions, which were only taken from a very particular side of the planet, from a very interesting geological area of the moon, but that might not actually be representative of the whole moon. We get some information about that from lunar meteorites, but obviously have limited context for those. there is the potential we might actually be able to get samples of the lunar mantle from one of the largest impact basins, the South Polacan Basin on the South Pole, surprised to find, of the moon, which might actually have excavated some mantle material. And actually getting, and that SPA is a target for one of the future Chinese sample returns. And I know there's a lot of people within NASA who are also, community in the US that are pushing for NASA to go to SPA as well. So there is a chance that we might actually get samples of the lunar mantle, which might tell us a lot more about the lunar composition, isotopic heterogeneity or homogeneity, as may be the case. And that, I think, is very exciting from a lunar scientist's perspective, although the politics will be wonderfully interesting. One of the big issues that I alluded to before is understanding the post-impact evolution of the system. And particularly if we're going to try and compare to geochemical evidence, we need to be able to link the physics and the geochemistry, which is only really just in its infancy of modeling. And that really is sort of a big focus, both from the geochemistry side and understanding the thermodynamics of multi-component systems, but also from the physics of dealing with what happens when you have vapor and droplets and an atmosphere of a disk that's condensing. So unlike astrophysicists, astrophysical disks where you have mostly hydrogen, which is lovely and does not condense and is static. In the Earth-Moon system, you have silicate vapor. Your majority material is silicate vapor, which can condense on a dime because it's trying to radiate at 2300 Kelvin. So it's a very unstable dynamic system, and understanding that is challenging. One of the more interesting observations I've not talked about, which I'm just going to mention here, is the recent observation that the Earth and the Moon are different in some isotopes, but not in mass-independent fingerprints, but in mass-dependent isotopic fractionation. So I'm showing you here, is the delta 41 potassium. So don't worry about this, but basically in kinetic or equilibrium processes, you can fractionate different isotopes by depending on the ratio of their masses. And what you've seen first in this paper by Wang and Jacobson, and subsequently for a number of different elements, which all seem to give contradictory answers, which is why I haven't talked about this in the main part of this talk, is that the moon is offset from the Earth and relatively consistent, seemingly in this study with itself. And this is very interesting because this gives you a way of tracing the dynamic, the kinetic, the equilibrium conditions that are happening in the lunar disk or synestia, and just subsequent to it, where you have an open system on the moon and the potential of fractionating different isotopes between the Earth and the moon. And one more thing, which is a very challenging thing to overcome, is that we need to somehow improve how giant impact models capture mixing. So most of the models we use at the moment are for these sort of simulations are what's called smooth particle hydrodynamics. And basically what this does is it divides up all the material into blobs and lets those blobs fly about, interact by gravity and pressure, and you actually end up with a simulation that looks more like this. So you can see all of the material. This is a cut through of the midplane of a collision. You can see all of the material is just in these blobs. And the problem is that there's no mass exchange or thermal equilibrium between all of these blobs. And so a lot of the processes that would be leading to mixing are not captured in these simulations. And as I will talk more about on Wednesday, mixing during the impact is essential to explain the isotopic similarity between the Earth and the Moon. And so being able to capture this in simulations is incredibly important. And that requires both new methods, but also a better understanding of the material properties, the equations of state of different materials and how they behave in impacts. And finally, one of the things that we need to look at is that we've explored end methods. We've explored the canonical impact, which is the lowest energy I presume, unless Jack's going to tell me you can also increase the angular momentum of the Earth Moon system through evolution, is the lowest angular momentum, lowest energy impact you can have between those two bodies. And we've explored very high energy, relatively high angular momentum scenarios. There is a large mixture in between that we have not explored at all. And so there is potential that there might be intermediate cases which are less challenging in terms of changing angular momentum of the Earth Moon system afterwards, but do help and aid in solving some of the dynamical and geochemical problems that we have with moon formation. So there's a lot of fun stuff to do in between, but I will stop here and we can continue discussion.
Thank you, Simon, for a very thorough overview of this complex and fascinating problem. We have time for some questions from the audience. A lot of the ideas about observation of the moon have been driven by observation. And in your what is next, you brought up some of them. And I'm wondering about some of the others that were not mentioned. Would you like to comment on them? I'm thinking, for example, of Earth, Venus, and exoplanets. Now, in the case of Earth, I think it's an interesting question as to whether there are actually differences. For example, in the case of oxygen, talking to geochemists, they will acknowledge some of these, but that's a possibility. And of course, there's also the issue of the core, which has oxygen in it, and does that have a different capital? In the case of Venus, it seems to me that's key to this issue that Nicholas Alpha brings up. Could we perhaps get capital for oxygen for Venus or other things that might tell us about whether the projectile that hit the Earth was similar to the Earth? There was a mistake, perhaps. I was one of those who participated in it, of thinking that we should scale this to the difference between Earth and Mars. But it now seems more likely that Mars is kind of special, and that one should be thinking about the terrestrial planetary zone. And then, in respect of your own ideas of high rotation and so forth, what do you think about exoplanets observationally? I'm not talking about isotopes, but about the dynamics of exoplanets, rotation states. Do you think that that in the next decade is going to give us guidance?
So that's a lot. Yes. So I think I agree with you that Venus is key. I didn't mention it because I think that in situ or sample return observation of Cap Delta 18 oxygen is probably a long way off. But I think exploration of Venus is really critical to understand why it's so different as a planet generally. But yes, this question of whether there was an inner isotopically similar and how similar was the inner solar system reservoir is key to understanding and testing Nicolas' ideas. I would still say that even if there is an isotopically similar impactor, tungsten is still an issue. And so I think Kaveh said this to me at one of my first conferences as a grad student. I was very confused. It's like, tungsten is key. And I was like, and then I now have come to fully appreciate that I think that this, because it is process dependent, and there are other isotopes that you can go after that are similarly process dependent, which could be very interesting. Understanding how similar, first, the constraint from late accretion on how similar the Earth and the Moon could be, or more importantly, how different they could have been to begin with. And so how much mixing you would likely require and how likely that is, I think is really, in terms of the isotopic similarity, really where we should be focusing. But understanding the heterogeneity on the Moon with samples that are away from the Apollo sites, particularly if we can get more basalts from the Moon, would be really useful, because we might just be measuring something that's incredibly special for some reason. Seems to look like the Earth, and actually there might be more heterogeneity which would both give you a clue as to mixing, but also test these sort of ideas of whether there are multi-generational moons and things like that. As far as exoplanets is concerned, I'm really excited because I think there is the possibility of observing post-impact bodies directly in exosystems. So I think that silicate-based terrestrial giant impacts, the post-impact bodies last for a lower estimate is hundreds to thousands of years. They might last a bit longer depending on what the moon is doing or moons are doing, but they're unlikely to be observed because of their very short lifetimes. However, massive ice giant collisions have the potential to actually survive their post-impact body for tens to hundreds of millions of years on simple scaling arguments to be tested by direct simulation. And so there is the potential, particularly now we are observing systems. There was a paper on Archive this week of a 26 million year old exosystem. If we can look at those such young systems, we might actually be able to see smoking guns for impacts, which would be an incredibly powerful constraint on the outcome of giant impacts. If not terrestrial, they will give us an insight into giant impacts in general, but also the architecture of those systems. If we can start to get some understanding, even for very massive super Earths, whether they have moons, what the likelihood of them having moons are, it would be a huge constraint on both the moon formation side, but also on the planetary dynamic side as the formation. So I think exoplanets really, there is a lot of danger in being carried away with the wealth of data and, I suppose, wealth, many N of data, but very limited actual information about the systems. But I think if carefully managed, they will be a very useful insight into the dynamics of planet formation in general, which will have a fallback on moon formation in particular.
Here, one second. That's on this microphone.
Okay, my question: after the giant impact, many small asteroid bodies are formed with the formation of moon. Why are not considered as moons orbiting around the Earth? And the second question: is there a possibility for another giant impact in the future?
So to answer your first question, so firstly, any material that's injected into orbit around the moon, the Earth, they have been shown by dynamical simulations that they very quickly accrete to a single body. Because of the different mass ratios, if you form two larger moons, you form them in a lot of these simulations, but their lifetimes are quite short. So one moon either gets ejected or the two merge. And it's been suggested that the Earth might have had two smaller moons that merged later in formation. You do also produce a lot of asteroid-like bodies and a lot of small dust vapor that recondenses that is not bound to the Earth-Moon system, that is ejected into orbit. And that material, its fate is really interesting because a lot of it will come back and hit the Earth and could hit it on relatively short timescales. But a lot of it also hits other bodies. So the fate of that material is very interesting, and it's been studied in sort of not particularly realistic simulations. So it'll be fun to go back and look at that as sort of what is the fate of that ejector. I forgot what your last part of the question is.
Is there a possibility for another giant impact?
Unlikely. So there is the potential that our system might go unstable, at which point we might get hit by Venus or Mars. The chance of that happening are very unlikely. I did once at a conference suggest we might try and deliberately plow Mars into Venus as a large experiment, but there didn't seem to be any takers. Or you might have an impact from an extrasolar planet. So we know that there are a lot of planets just wandering between solar systems, but again, the sparse population of those bodies makes it extremely unlikely. And it would be, we'd be dead.
One last question from the audience, please.
I'm an economist, but what struck me was the uncertainty associated with the different models. I mean, the results seem, all over the place. And I was wondering if there's a room for robust modeling, that engineers do, where you have model averaging, for example, is one approach. You have penalties to different models to correct for misspecification, sort of entropy type penalties. And I was wondering if you considered, I mean, this is sort of done in economics now, but our data are, well, maybe our data are just about as bad. So I was wondering if you consider this type of approach. Yes, the models are similar, ill-fitting.
Yeah. So we could take an approach, run a large number of simulations and look at the statistics. And we do. We try and we do model and try and look at the systematics of how different impacts affect the outcome. The issue right now is that, frankly, I don't believe our models. I know that sounds very pessimistic, but there are a lot of fundamental issues with our understanding of how the materials behave that need to be improved before we can really think about taking that sort of approach, particularly for the actual formation, the models that actually model the lunar formation. We have huge issues with the fact that we are dealing with microscale physics, droplet formation, cloud formation, on bigger than planetary scales. So we have the same problems that the climate dynamicists have, with a lot less computational power and understanding of those mechanisms. Experimentally, it's almost impossible to explore the vapor side of the liquid vapor phase boundary, just because you have no way of containing it in the laboratory. And so I feel that those uncertainties, there are ways we can address them and improve them. And I think that's, before we start to look at more statistically average models, I think that's sort of a more fundamental thing to deal with. But yeah, in the future, particularly with improved computational power, it's a feasible way of approaching it.
So Simon will be with us for the week, and one of the highlights of the workshop is his lecture of the recent models that talked about the size scale and politics dealing with semesters. Please join me in thanking Simon. While Jack is setting up, I can give you an anecdote. So you heard Simon referring to the work of Robert Campbell. If you're as blatant as my friend Fufu, looking at the panel that you have gathered, you may say, ما في نسوان في هذا المجال تبعكم, which is rather roughly Lebanese to say, where are the women in your field? And of course, we have wonderful women planetary scientists who have shaped our understanding of lunar formation. And the first thing we did is to attempt to contact them, and they're so influential and so busy that it was very hard to pin them down. They're busy with administrative work, busy with family, and overworked on many aspects, which is the face of very successful women around the globe. So Robin is with us through her work, though she wasn't able to be with us in person, and certainly Sarah Stewart, and her contributions will be featured later on through Simon's talk, among others. Okay? Nice. So next is Jack Wisdom, talking about the evolution, tidal evolution of the Earth moon system. So this is a review. Just a few words about Jack. So I first met Jack through his works as an undergraduate student. People were very excited about his work on chaos in the solar system, particularly in 86, 87, around his work in Hyperion. My mentor around the time said, Jihad, here, check this out. This looks very interesting. And I said, okay, I want to be working in that direction. So I first went and met Jack's advisor at Caltech, who extended an invitation to join, and that was Peter Goldreich. And after waiting a long time, I said to Peter, whom we are very unfortunate not to be able to have with us here, though he will appear again in various lectures. During the meeting, Peter said, why are you coming to me for that? Why don't you go directly to Jack? This was his ideas, so you go work with him. That was very much Peter-like, and eventually I ended up at the applied math program at MIT, and interpolated between planetary science and had the pleasure of working with Jack on a number of things. Of course, he's one of the leading dynamicists, largely revolutionized the field and the way we think about it in terms of appreciation of chaos and shaping the evolution of the solar system, giving us one of the most beautiful examples of such chaos in terms of the spin of Hyperion, and then going on to lead in a variety of ways, partly numerical, partly theoretical. And here we're having with us for 3 lectures, elaborating on work involving the tidal evolution of the Earth-Moon system, partly overview of the physics today, and eventually detailed models involving taking the moon from origin to the present, having spent quite a bit of time trying to understand what the present says about the past. So please join me in welcoming Jack Wisdom.
Thank you, Shahad. That was a very nice introduction. Thank you also for the invitation to come here, and I'm very happy to be here and be in Lebanon. Shahad has said, I think twice now, I'm giving 3 lectures. The first one is just a review of tidal evolution, because we have to get the moon from those formation scenarios to where it is today. And so it's a little review and a little a review of some very old works in this lecture. And Shahad played a big role in all these early works, so I put his name there. I hope he doesn't mind. The second lecture is on tidal evolution of the moon from a high angular momentum state, which was suggested by Mattia Chuk and Sarah Stewart. And the evection resonance plays a big role in that. And so that's the second lecture. And then the third lecture is an elaboration, more recent investigation of Mattia Chuk's next invention, which was the high angular momentum, high obliquity initial condition for the moon. And so, the last one has some new work in it. The other 2 are just review talks. So, and they go in and out of equations. I hope you don't mind. This is first about tidal evolution, and then old results on the history of the Earth-Moon system, and 20 years old. Yes, anyway. So here's, I'm going to talk about tides first. So the gravitational potential between a point mass, a perturbing point mass, and say the Earth, is just the potential energy is just the sum of Newtonian potential energy for all the constituents of the body. So it's a sum over m alpha. And the distance between m alpha and the tide raising, or the perturbing body, is d alpha. So this is just an expression d alpha using the law of cosines. The size of bodies are small compared to the distance between the bodies, so you can expand this in the ratio of the distance from the center of mass to the mass element, and you get a rapidly converging series involving Legendre polynomials. So there you go. Now, the first few Legendre polynomials are just a constant x, and 3 has x squared minus a half. The first term gives the Newtonian potential energy between 2 point masses. The second term is 0 if you take the reference point to be the center of mass. The third term is this expression, which is the key one. And the quantity in parenthesis is the tide raising potential. It is not only the potential that raises the tides, but it also gives rise to, if the body has strength, it gives rise to the torques on the body. So an out-of-rounded body like Hyperion is basically torqued by this term. And this also gives rise to tidal raising of tides. So in general, the tide raising potential is just this sum, but we only focus on L equal to 2, the first term. So a body distorts when a tide raising of potential is applied to it. And this distortion creates an external tidal potential the distorted mass creates its own potential outside. And then we can derive tidal forces from this external tidal potential. And again, I'm going to restrict to just the L equal to 2. The potential outside is dominated by a potential with the same spatial pattern as the tidal potential that's applied. So in this case, it's proportional to this P2 factor of the cosine S. But strictly speaking, there are other smaller components. For instance, Jupiter is distorted by a tidal potential, the centrifugal tidal potential, but there are many moments besides the J2. So the Love number, K2, is defined as the ratio of the tide raising potential to the potential of the mass that is just of the distorted body at the surface. And then you have to extrapolate this tidal potential of the surface to other places. So K2 is this ratio, it's a dimensionless number that makes the ratio between these two potentials. And then the exterior potential is a solution of the Laplace equation. So this is the potential at a position R and cosine S, given a tide raising potential here, and then decay because it's a solution of the Laplace equation, and it's proportional to K2. I'm going to get this as a picture soon. So anyway, there are several Love numbers. There's another Love number called the displacement Love number. So the surface of the Earth is distorted by tides on the solid Earth. Of course, there are tides on the fluid Earth too, but I'm speaking mostly about tides on the solid Earth. So the tidal potential divided by the surface gravity multiplied by another Love number gives rise to the surface displacement as a function of angle. And Lord Kelvin in 1863 showed for a homogeneous elastic body with rigidity mu, these Love numbers are 3/2 divided by something involving rigidity and 5/2 divided by something involving rigidity. And more generally, the Love numbers depend upon the interior structure of the planet, even if there's no rigidity. So what are the Love numbers? So for the moon, the Love number is K2 is measured to be 0.024 by laser ranging, and probably also by Grail analysis. And H2 is measured to be 0.037. These are marginally consistent with this ratio of 5/2 that you get from Kelvin's formula. For the Earth, the Love number is 0.3 or 0.6, K2 and H2. And then for the gas giants, you have Jupiter 0.379, calculated by Gavrilov and Zarkov in 77, and then presumably improved by Juno and Cassini. And the measurements of these Love numbers in the moments give rise to modern understanding of the interior structure of Jupiter. So if you, as I said, there are tides on the solid Earth, the displacement at S equals 0, that's the line between the perturber and the Earth. If you evaluate that expression, you get this simple expression. So the distortion of the surface divided by the radius of the planet is H2 times this dimensionless quantity involving the masses and the radii. And if you evaluate this for the Earth and the Moon, you find that the tides from the Moon on the solid Earth give rise to a twice daily change in height of about 20 centimeters. So you go up and down, as you rotate under the Moon, you rotate up and down twice a day by about 20 centimeters, and twice a day under the Sun of about 10 centimeters. How are we doing? Completely lost. So I'm going to introduce a tidal model called the Mignard tides. The tidal model is very simple, and it's very commonly used. It's used in 99% of all the works on tides. It's used in studies of exoplanets, everything. So it was invented by Francois Mignard in 79, but earlier by George Darwin, who is, I believe, the son of Charles Darwin, and also by Pete Hutt. And I don't know if Pete Hutt knew about Mignard's work, but they had developed around the same time, so it's often called the Mignard-Hutt model. The basic idea is that there's this body orbiting, moving at velocity v and a relative distance r from the center of mass, and the planet is rotating possibly about some oblique axis. And the idea is that this tide raising potential raises a tide, and it's a coherent tide. So it's just one tidal bulge with a P2 shape. But tides are dissipative processes, and dissipative processes, the response lags the forcing. And so if you let, again, the equations are going to be over soon, so sorry. If you let r be the distance between the moon and the Earth, the rectangular coordinates of the moon to the Earth, then the tide was actually raised at a time earlier. So when the moon was at this place, t minus delta t. But between the time the tide was raised and the current time, the tide was rotated because the Earth rotates. So the actual, the effective place of the tide raiser is given by that expression. And then you linearize in delta t, you get this expression. The v arises because I'm doing derivative of r with respect to time and multiplying by delta t. And you plug this into the tidal expression, tidal potential, and you linearize again, and then you get finally the force, the tidal force. So, so this is the expression for the tidal force in the Mignard model. It involves a high power of the radius. It involves the K2 of the Love number, and it involves the square of the mass of the perturber, a high power of the radius of the Earth, and then a complicated expression involving the velocity, the rotation, and the displacement to the Earth. And then if you do r cross f, you get the torque, and it's another complicated expression involving the rotation rate, the distance, and the velocity of the perturber. And then the torque on the body on which this is the torque on the moon. The torque on the Earth is the equal and opposite by conservation of angular momentum. And so, it's a complicated expression. Now, this was done in the 70s, but earlier by Darwin, George Darwin. But Darwin developed a more general theory of tides, and it was given a compact form by Kolla in '64. And the basic idea is that you Fourier transform the tide raising potential. So the fact that the orbit of the moon around the Earth is complicated means there's a complicated, many different components in the tide raising potential. You Fourier transform that, and then you incorporate dissipation by adding a phase delay to each component of the tide that's raised. Then you develop the exterior potential due to all those tides, and you get the force. So it's a nice theory. It seems to make sense to me, but it has a problem that it has an infinity of phase delays, which are unknown in general. It would be nice to have, say, a physical model of the tidal response of the planet, so you could set the phase delays by some physical model, but we don't have that yet. So Goldreich in '66 argued that because seismic dissipation is independent of frequency, one should take all these tidal phase delays to be equal. So that's called the constant Q model. So we have the Mignard model and the constant Q model. So what's the Q of an oscillator? Q is a measure of dissipation in an oscillator. Here's its definition. 1 over Q is, this is the integral of the rate of energy dissipation over one cycle of the oscillator divided by the energy stored in the oscillator. We can evaluate this for a damped driven oscillator. So there's a driven oscillator, the driving A cos omega t. And here's the solution. It's just a different amplitude multiplied by phase delayed omega t. So you take this and delay it by a phase delta. And here's the solution of a damped driven oscillator. If you evaluate that expression for the Q, you get this expression. So 1 over Q, doing all the integrals and dividing through, you get this expression for 1 over Q involving the driving frequency, the natural oscillation frequency, the amplitude of the dissipation, and the phase delay. Now, if the dissipation is small, you can ignore this term and you get this expression. If the driving frequency is small compared to the natural oscillation frequency, you get the this expression, and then you approximate that by delta. And so you get the phases are all just 1 over q. So a constant q model means we're going to take all of the phases to be equal. So what are what's known about the Qs in the solar system? Not very much. The Q of the moon is known at 2 periods. The Q of the moon at 1 year is 39, and the Q at 1 month is 37. And notice that this is approximately independent of frequency. So 70 years after Goldreich, 50 years after Goldreich proposed that the Q should be independent of frequency, it's actually confirmed by the available data. So anyway, the Q of the Q of the Earth is around 12. It's dominated by dissipation in the Earth's oceans. The Q of Mars is around 85. This is measured by looking at the shadows of Phobos move across the surface of Mars. Q of the giant planets are larger, so these are determined by looking at the configurations of the satellites, how close they are to Jupiter. And you place limits on the Q of Jupiter, so Jupiter has to be bigger than 25,000. Saturn has to be bigger, by that argument, bigger than 18,000. And then we place limits on the Uranus Q by looking at possible configurations of the satellites of Uranus. Astrometric measurements of the motion of the satellites of Saturn have given a lower Q of Saturn. And so this is lower than is possible by the proximity of the Saturn satellites to Saturn. And so that probably perhaps means that the Saturn satellites are younger than the age of the solar system. So here's, as I said, it would be nice to have physical models to predict what the phase lags are. So here are a variety of physical models. And here's the data. Here's the 1 month and 1 year Q, which K2 over Q. And you can see that the physical models generally don't go through the data. There are two physical models that do go through the data, but they have extra parameters that allow them to be adjusted so that they do go through the data. And so the only model that actually fits the data without having to adjust physical parameters is the constant Q model. So I'm going to generally stick with the constant Q model. It would be nice to have results that are independent of tidal model, and I'll show you some, but in some cases I'm going to not have the liberty to have examined all tidal models, and I'm going to just show you constant Q results. I'd like ultimately to show you constant Q and other models. Okay, so simple illustration of Mignard tide is if we make things into a circular orbit, circular uninclined orbit, then the tidal torque is this expression. This depends upon the difference of the rotation rate of the Earth and the orbital frequency of the Moon. So the angular momentum of the circular orbit is this expression, and you equate the rate of change of the semi-major axis of the Moon to rate of change of the torque to the rate of change of the angular momentum to the torque. You get an expression for A dot, and this is how fast the Moon is evolving outwards. And it depends upon, again, the K2 of high power of the radius of the Moon's orbit, mass ratio of the Moon to the Earth. And then this factor, so if the Earth is rotating rapidly, then the Moon evolves outwards. If the Earth is rotating slowly, the Moon evolves inwards. So Phobos, for instance, a satellite of Mars, is evolving inwards and will soon crash into Mars. Now, if we identify the quantity in square brackets with the phase delay, we get this expression, which is a very commonly used expression for tidal evolution. People abandon the Mignard model and go to this expression and use it for constant Q. And then now you just have the sign of whether the rotation rate of the Earth is faster or slower than the orbital rate. Okay. So it's this kind of expression that's used to establish those limits on the Qs of the giant planets. So you can also derive this expression I just showed using the constant Q model, but that's a separate thing. So now I'm going to turn to pictures. So you can wake up now. There's a classic paper by Goldreich, I call it classic, in 1966 called The History of the Lunar Orbit. And then Shahad and I did 2 papers, works on the moon, 94, 98, and I'll describe the main results of each of these papers. So here's the title page of Goldreich's 66 paper. So the assumptions that Goldreich used in doing his tidal model, he included only the moon, the earth, and the sun. He assumed all the orbits were circular, and that he averaged over everything in sight. He made the circular orbits into circular rings, and then the moon's orbit precesses around the Earth, and he averaged the equations of motion over the precession timescales and added several tidal models. And then he found the first evolution of the Earth-Moon system. So this is the results are usually plotted in terms of the distance from the Earth to the moon. So the moon's is now at 60 Earth radii. This is the obliquity, that's the tilt of the Earth's spin axis to the Earth, the orbit of the Earth. And at the present, at 60 Earth radii, the Earth is tilted by 23 degrees. As you evolve backwards in time, the moon gets closer to the Earth. And then for distances closer than 20 to 25 Earth radii, the moon's motion becomes more complicated. It becomes dominated by the Earth's equator rather than the sun. And this is called the Laplace transformation, Laplace transition. And this is showing the maximum and the minimum obliquity. The obliquity of the moon, of the Earth oscillations, the obliquity of the Earth oscillations showing the maximum and minimum. And so you find that the initial primordial obliquity of the Earth was maybe around 10 degrees, and it evolved to 23 degrees today. This is basically just a consequence of angular momentum conservation. As the moon moves outwards, it gains angular momentum, and that extracts angular momentum from the z component of the Earth's angular momentum, and that makes it tilt over gradually with time. So in the past, it was more upright. This is showing the inclination to the ecliptic of the moon. So the moon is inclined by about 5 degrees to the Earth's orbit today. And then you evolve that backwards in time using this model. You find that it begins to do some wild oscillations as it gets close to the Earth. But if you plot this in a different way, plot it versus the inclination of the moon relative to the equator of the Earth, then out here it oscillates up and down with respect to 23 degrees by the 5-degree inclination of the moon. And so there's an oscillation. But when you get close to the Earth, the inclination of the moon settles down and it becomes highly inclined relative to the equator of the Earth. And in this simulation, in this model, the inclination to the equator grows as you get close to the Earth. So there are 2 problems are revealed by these calculations. One is called the timescale problem. I didn't show you any plots versus time, but if I had, you would find that the moon was close to the Earth about 1.5 billion years ago, and extrapolating the current values of the dissipation in the moon. But we know the moon is old, 4.5 billion years, and so there's a problem with the time scale. And most people believe that the tidal parameters varied. That's a recurring problem. We don't know how the tidal parameters vary with time. So they may have, over the last few 100 million years to 1 billion years, they may have been the same as they are today, but early on they might have been different. And presumably, the tidal parameters can change because the continents drift. That changes the resonances of the ocean and the ocean, so the tidal parameters change. So the inclination problem, the fact that you start with a 5-degree inclination today, and it gives rise to, large inclination relative to the equator early on, is the inclination problem. And so the inclination problem excludes all the scenarios that Simon mentioned. It excludes Darwin's fission, excludes co-accretion, it excludes all the giant impact scenarios. The only thing it's consistent with is capture. And so that was an early possibility as a result of Goldreich's theory. Questions so far? Jihad and I, we had re-examined this problem. Goldreich used a non-Hamiltonian model for evolution. We used a Hamiltonian theory. And then we did the same, we incorporated all the same approximations Goldreich did, except it was Hamiltonian. So all the orbits are circular, and we averaged over the precession timescale of the moon's orbit. And then this was supplemented with a simulation of the Earth-Moon system in the presence of the chaotically evolving solar system. And so we used a symplectic integrator method, and then we used Jihad's Lee-Poisson method for the rotation of the Earth, and then we used Mignard constant delta T tides for no better. Okay, yes. So first we did the Hamiltonian average theory, and basically we reproduced all of Goldreich's results in this more complicated theory. So here's the obliquity of the Earth starting at 23 degrees, going down to 10 degrees as the moon gets close to the Earth. And this is, the various curves here are different tidal models. They're the Mignard tides, the Kalla, Goldreich, constant Q tides, and then a tide no one considers anymore called the McDonald tide. And basically you see that the results are independent of tidal model, which is a good thing. Then here's the inclination of the moon starting at 5 degrees, growing to complicated behavior close to the Earth, and then the large mutual inclination to the Earth's equator is reproduced. And it doesn't depend too much, again, on tidal model. So, so all the uncertainties in how to choose the phase lags are not relevant. What is more relevant is including all the tidal effects. If you include the dotted line is just including the tides between the Earth and the moon. The dashed line includes tides on the Earth raised by the sun. And then the solid line is including the tides, including those effects, plus the tides, what are called cross tides, where the sun raises a tide on the Earth, but that tide affects the moon. And so this was discovered to be important by Goldreich, and we confirmed that. So you can see including all the tidal effects makes more difference than changing the tidal model. And then Shahad wrote a nice program on evolving the Earth-Moon system with the chaotically evolving planetary system with the Mignard tides. And here's a typical result. So this is the obliquity, the mutual obliquity of the Earth-Moon system plotted again versus semi-major axis. And this is a stroboscopic view of the results. So there's an oscillation in this mutual obliquity. And then when you get close to the Earth, it settles onto this high mutual inclination state. Now, I've never convinced anyone on this too much. So I probably won't convince you. But if you look at this closely, you'll see there's a little glitch here. Can you see the glitch? You can. So we noticed a little, there's something that was wrong with Goldreich's by doing full simulations. And we thought maybe including all the planets would matter. Maybe, who knows what would matter. But we basically reproduced everything in Goldreich except that little glitch. And so, so we investigated that glitch, and we found that what was happening was that the Earth-Moon system was evolving through a resonance with the sun, called the advection resonance now. This is a resonance where the precession rate of the Earth's perigee matches the year. So the motion of the Earth around the sun. And so, so we investigated this. So here's the advection is when the precession of the perigee matches the year. And then analytically, it's a second order resonance proportional to the square of the eccentricity of the moon times the cosine of twice of a resonant argument. And this angle is the perigee longitude minus the longitude of the Earth around the sun. And if you go forward in time rather than backward in time, you can be captured into the evection resonance and get large eccentricities of the moon. And so this shows one simulation without any dissipation in the moon. And then there's some analytical expressions that reproduce the result. Now, tidal dissipation is large eccentricity. And so the eccentricity is large here. We can expect the moon to be tidally heated by a large amount. And if you raise the temperature by the moon by a large amount, it's going to change the properties of the moon. It's going to partially melt the moon. And so what large tidal heating in the moon does is damp the eccentricity of the moon and also decrease the semi-major axis of the moon. And then that allows a subsequent passage through the evection resonance and a resonance which Jihad labeled the eviction resonance. It's the evection with the E replaced by an I because it affects the inclination rather than the eccentricity. I think it's a nice name. So if you look at this scenario, you can evolve as in a giant impact scenario. You can start with zero mutual inclination of the moon relative to the equator of the Earth. You can evolve through this dance through various resonances of evection and eviction. And it turns out that you can excite the inclination of the moon to join the trajectory that is calculated by all the earlier work. So, so remember in Goldrecht's work, this shot off to large mutual inclination, and now we find a way of jumping onto that trajectory at a later time. So it seems like a nice result. And so here's some proposed solutions of what's called the mutual inclination problem. And one is this evection scenario, which we found could reproduce typically between 9 and 13 degrees, independent of all the parameters you put in, and you need 12 degrees to explain the moon. So that was a positive aspect of the scenario. It naturally explained the inclination of the moon. Another scenario is a proposal by Ward and Knapp that there were resonances between the disk left over around the Earth as the moon moved away from the Earth, and so resonances between that disk and the moon excited the inclination of the moon. I don't believe this one makes any specific predictions. And then maybe there are subsequent collisions that caused the inclination of the moon. And then Matyachuk has come up with yet another way of explaining the inclination of the moon in this high obliquity, high angle momentum scenario. And so I think that's it. That was pretty quick. So, and if anyone understood any of that, you can ask questions. So.
Yes, for those who didn't understand anything, you have time for a lot of questions. Yes, Colin. Let me pass this on, please.
Can I just shout?
No, it's I think they need it for streaming or whatever.
I would have assumed there's a fair amount of dissipation because of the interior of the Earth not being solid and rigid, as opposed, you mentioned oceanic tides.
Well, there's going to be dissipation in the Earth and the Moon, but the eccentricity of the Earth is dominated, the eccentricity of the Moon's orbit is dominated by dissipation in the Moon. You can directly relate the E dot to dissipation rate in the Moon.
The distinction he's making, Jack, is between dissipation on the oceans and the crust versus dissipation within the interior of the Earth. If you can make the distinction for him, it would be.
Well, I don't really have much to say about that. Yeah.
That's Jack. Any other questions? So Jack will build on that to talk about more recent, relatively more recent results tomorrow and the day after. And we have also Mattia who will be talking about his work, his scenarios. So we're pretty much looking forward to that in the next couple of days. Any other questions? Yes.
In one of the graphs, if you can go back in the slides, yeah, we can always notice this dip to zero. Why is that?
Why we started at zero,
Yeah, then we dip back.
and then we go through this dance of resonances, and we join on to the scenarios that everyone else has gotten later on.
Yeah.
So what was the question?
We dip back at the zero at almost 19 on the x-axis. We can go back to a zero angle.
She's referring to that cusp at 19 radii.
Yeah.
Oh, well, this is in the phase where, in this phase, you're dominated by the perturbations from the sun, and then early phase, you're dominated by perturbations from the oblateness of the Earth. And there's a transition between the two, which Jihad has recently worked on, called the Laplace transition. And so I don't have anything more to say.
So it straightens back up. Thank you.
Perhaps this question will be answered later, but let me try it now. In these resonances, like the three-body one that is invoked to extract angular momentum from the Earth-Moon system, there is an uncertainty about the evolution, it would seem, because of an uncertainty in the tidal parameters, how Q changes and so forth. And my question is this: is there any general statement that can be made independent of the details based on conservation of energy, or some statement of that kind? What I'm getting at is that you can have two different stories, one of which involves Q getting very large and the dissipation per unit time becoming small, and another story might be where Q stays low and the dissipation per unit time is high, but the two stories could conceivably be similar in terms of the total energy dissipated if you had some general theorem that said that you had to get rid of a certain amount of energy based on the eccentricity that is mandated by the mechanism, or something like that. As you know, eccentricity translates into a statement about orbital energy and therefore about how much energy might need to be dissipated. And of course, this is relevant to the origin of the moon because of the issue of how hot the moon may have gotten in an impact, in a resonance event. I understand that it's more complicated because if I do the heating fast, it may get a high temperature, and if I do the heating slowly, then you may lose that energy. But I still wonder, is there any statement of the kind I'm imagining, or is it just unavoidably complicated?
I don't know of any constraint on the energy. The angular momentum, of course, provides constraints, but I don't know of a constraint on energy that could help you narrow down the scenarios.
Okay, so if there are, do you have a question, Mattia?
Maybe we should answer the question about the plot, because these plots will be coming up throughout. So I think you would be the best person to do that. Well, to explain why the plot looks like that, what happens at zero, like why it goes.
What happens at that actual
Yeah.
point of transition?
Yeah.
This is the transition in terms of the Laplace surface, where the moon essentially goes from being Earth dominated or dominated by forcing from the Earth oblateness to a stage where it's actually dominated by the sun's perturbations. And the actual location you're seeing here, you have to think of this plot as describing for you the actual oscillations that are taking place rather than an establishment of any mean value of the inclination that may suggest that we're going back to where we were. So what we're seeing is the moon is undergoing oscillations with respect to the equator and then the ecliptic. And this is what the plot is showing. So this is not a steady state that you're observing. What you're observing is an oscillation around the mean, which is ultimately evolving to approach the ecliptic eventually in time. Okay? Did you have anything more to add? Or any question? Or any constraints on energy, perhaps?
I agree with that.
Okay. So with that, we'll have to break for lunch, and we'll resume at 2 with what I think will be a beautiful lecture by Professor Stevenson on the curious asymmetry in the moon. I'm sure you've all wondered about that, and we'll hear his thoughts on the problem around 2. And then we'll take it up from there on historical reflection on the evection, and eventually a keynote lecture by Professor Saliba at 4:30. And if you want to avoid all that, we'll have a reception by 6:30 or so, and you're welcome to join us for that. Okay.